Hello everyone, I am Madhukar Yerraguntla, a PhD student in the Department of Computer Science, IIT Delhi. This presentation is on security types for synchronous data flow systems. Our lives today are permeated with IoT devices. They are present from cars to smart lights to even pacemakers. However, vulnerabilities have been exposed time and again in these devices, ranging from minor annoyances to outright life-threatening. The causes of these issues in IoT devices can be broadly classified as unintended connections between modules, no proper secure information flow architecture, using languages with constructs that are unsafe and difficult to reason about, like pointers in C. The pacemaker model that was recalled was using the same channel to communicate vitals and also sensitive information. Hackers could exploit this remotely and drain the battery using just a mobile phone. The approach we suggest is secure by construction. We write IoT programs in an intuitive and safe language, prove that the basic nodes are secure individually, then verify that when these nodes are reused in a larger system, the security is maintained. This property, called compositionality, is often not upheld in design practices followed so far. Finally, we verify that the compilation to a low-level language like C preserves security property and give a machine-checked proof of this translation. Lustre is a synchronous programming language where events, including computations, happen synchronous to a clock. Lustre programs are made of nodes. The figure shows a counter node in Lustre and its semantics. Lustre programs run forever and produce streams of values whenever the input streams are present. The only missing element for Lustre to be a modeling language for IoT is a framework to reason about secure information flow, and that is what we describe in this work. We express the notion of security using the property of non-interference. Non-interference says that changing the values only on high security inputs does not show a change in the low security outputs. This way, we prevent secure information from leaking out. Since Lustre programs run forever, this might seem difficult to check. However, we show that this property can be inferred statically. Given a lattice of security levels, the program streams are assigned with type variables that map to security levels. The lattice can be as complex as necessitated by the application. Our analysis expresses minimal requirements of secure information flow using these type variables. Finally, we verify that these requirements under the security lattice mapping are satisfied. The type system reasons about security at each syntactic level. Expressions like the when sampling operation shown here generate a new stream. Suppose E has the type delta and X has the security type alpha, then the stream E when X equals true has permissions of both alpha and delta. Equations generate a constraint that says the security type of the LHS variable beta should at least be as high as that of the RHS expression. At node level, the analysis generates a node signature that conveys that inputs on a clock are converted into outputs provided the constraints from the equations are satisfied. The main result of our work states that well-typed Lisp programs exhibit non-interference. What does well-typed mean? Given that our analysis of the top-level node in the program returns this node signature, and given a security lattice mapping, if the node signature constraints are satisfied on the mapping, program is well-typed. By the main theorem, such programs exhibit non-interference and hence are secure. Otherwise, there may be a flow that violates this property. For more information, please refer to our Memocode 2020 work, Security Types for Synchronous Data Flow Systems. This work received the Best Paper Award at this conference. The preprint of our upcoming work in ICTAC 2021 is also available on arXiv. Thank you for your attention.